All right, let's take a look at another CSES graph problem, shortest routes 2. So what's going on here? We have a graph with n vertices and m edges, and we're going to get q pairs of vertices, and we're supposed to give the shortest path between them. And the edges have weights, and they are bidirectional, undirected graph. So the constraints are important here. N is only up to 500. So in the previous problem, n was 100,000. Here it's 500. But q is 100,000. So we're given 100,000 pairs. And also m is up to n squared. So like this graph is dense, right? There could be like an edge between every pair of vertices. The weight's up to a billion, that doesn't matter so much. So this problem is sort of designed to show off the Floyd-Warshall algorithm. So let me talk about that for a second. So Floyd-Warshall is an n-cubed algorithm, and it gives you like a matrix, which is the shortest path between any pair of vertices. And it's kind of like a DP, basically. So the code is very short, which is kind of cool. So what it's doing is it's computing the shortest path that only uses some intermediate edges that it's going to sort of build up over time. So initially, it's like just the direct edges. And then it says, OK, well, what if I allowed you to go through vertex 0 in addition to a direct edge, right? You could either go directly or you could go through vertex 0. And then it says, OK, well, what if I allowed you to go through also vertex 1, right? You can either go directly or you can like go through 0 to 1. Right, so anyway, the point is that the shortest path, like adding on a new vertex, is either the oldest shortest path, or it is going to that new vertex, right, from I to the new vertex, and then from that new vertex to J. So that's what this is doing. This is taking the minimum of the current shortest path and the shortest path going through the new vertex, going through the new vertex. And so if you do that for all the values of k, then you get the shortest path going through any vertex, which is exactly what you want. And so this is n cubed, sort of very obviously, because there's like 3 for loops. And the code is very short, you'll notice. And yeah, so there's this like somewhat complicated DP idea going on, which I've just explained, but like the implementation is very slick. So let's code it up and see how that looks like. Shortest routes to, so we'll do this one in C++. So n and m, and very unusually, we are not going to use a adjacency list. We're going to use a so-called adjacency matrix, where you write down like for every pair of vertices is there an edge between them. This is, usually you don't do this because like it's really bad if m is small, but m can be up to n squared here, so it's actually fine. And we're going to want some concept of infinity. So a safe concept of infinity will be like 10 to the 15. You just want it to be longer than any possible path in the graph, and the longest path in the graph is 500 nodes long times 10 to the billion per edge. So 10 to the 15 will be 20. Okay, and then for the edges, so we read in the edge, which is ABC, it's two-way, bidirectional. And there might be multiple edges between two vertices, so that's why we're taking like a min. That's why we're also starting with infinity, kind of. Right, infinity is the identity for min. That is, if you min with, if you get a real edge, it'll replace the infinity. That's what I mean by saying that it's the identity, is that it gets washed out by anything real. Okay. We also want to set the diagonal to 0, because you can get to yourself immediately. And now we can run Floyd-Warshall. Okay, so for every intermediate vertex, k is 0, k is less than n, k plus plus, okay. 0, I is less than n. So for every starting vertex and for every ending vertex, the distance from start to end is the min of the current distance from start to end and the distance going through the new intermediate vertex k, right, which is just the distance to k and then the distance from k to j. And so now dij, distance from I to j, using middle vertices 0 through k. We probably wanted to read in Q on the first line. Yeah, sure. Okay, so now that we've actually computed the shortest paths, we can just read in the queries and answer them, just by looking at the value. Again, we need to zero index. Okay, and there is a detail here, which is it says print -1 if there is no route. Well, how do we tell if that happened? It's if it's still infinity. Right, it's infinity. If it's still infinity, that means that there was no edge between them. And also, there was no like intermediate path between them, right? This min never kicked in. Yeah, so infinity is, I don't know, the code for there not being any path. And instead of, infinity, we're supposed to write -1. So fine. And that's it, actually. So the core algorithm is like literally 4 lines long. So that's kind of neat, right? It's just these triple for loops. And k goes on the outside, sometimes hard for people to remember. But if you think about the DP that this is actually doing, it's like somewhat clear that k needs to be on the outside. If you just try to memorize the 3 for loops, it'll get confusing. We need vector, we need stud, we need LL. Should be it. Okay. Five, 5, 8, -1, 3. How about that? Cool. Yeah, so that's Floyd-Warshall. Very short algorithm. It does need a little bit of setup, right? So you need to have this like matrix. You're supposed to write infinity if there's no edge between them. Just the minimum edge weight if there is an edge between them, and 0 for a vertex to itself. And then you just run these 4 lines of code, and now you have the actual minimum, right now, D is basically like the adjacency matrix, or just like the edge weights. And at the end, D is the minimum distances. And so we can just read out elements of D to answer the queries. And the one, I guess, special case is that there not being a path is represented by the value still being infinity. So I'll put -1 in that case. So that's Floyd-Warshall. It's more niche than Dijkstra, but it is a good thing to know. It's simpler than Dijkstra if you come across a problem that actually that is good for, right? That you can afford n-cubed time. That's the main downside of Floyd-Warshall, is that it takes n-cubed time. Whereas like if this graph was sparse, right? If m was about n, then just running Dijkstra from every vertex, which would also compute you all the shortest paths, would just take like n squared time, approximately. Nm log n. But if the graph is dense, then this is good. So that's Floyd-Warshall.